I'm James Parker, and I'm a researcher at Galois. Today I'll be talking about some work in progress towards verifying the Jolt zkVM. This is joint work with a great team at Galois and our collaborators at University of Cambridge and Lindy Labs. So to give some motivation for this work, I think we all know how great zero-knowledge proofs are. In the context of blockchain, they're used to allow smart contract updates and transactions to be validated quickly. So this gives us improvements in terms of gas fees and improves throughput. So one problem is that zk statements are very complex. Oftentimes they're very large and they're hard to verify. So you want to have some assurance that they're actually correct. So our solution to this problem is to formally verify the front-end statements that these zkVMs make. So in this effort, we're focused on verifying the Jolt zkVM. In Jolt, their front-end statements are composed of R1CS, lookup tables, and the composition of lookup tables. At least I personally think this is one of the most promising VMs. It has great performance, and I think this design and architecture is much more amenable to formal verification and also performance. Jolt emulates the RISC-V 32-bit IM machine, and it's developed by Michael, Sam, Rusu, Srinath, and Justin. So just to give like a high-level goal of what we aim to do in the long term, our main goal is to prove soundness of the front-end system. So this breaks down into two main theorems. The first is that for all witness values, if the witness does not correspond to an actual machine word, then basically the circuit should reject that, since it's not a valid instantiation of the machine. And then if the witnesses do correspond to machine words, then the inputs and the outputs of the witness should correspond to the RISC-V semantics. And again, here you can see this statement sort of represented visually, where you have the inputs and outputs of field elements at the top, they're passed into the circuit, and then at the bottom you can see they're converted into machine words and then run through some reference RISC-V semantics. So this is the general approach that we're taking. We're currently in stage 1, which is in progress. So the first thing we're doing is that we're defining a reference RISC-V semantics. So we're using a tool called Sail for this. The next thing we're doing is that we're implementing a DSL in Lean for representing zk circuits. We call this library zkLean. And then the third thing we're doing is we're implementing a tool to automatically extract the circuits from Jolt, and then we're representing them in zkLean, so then we can prove properties about them. In a next stage, we are going to aim to prove that the arithmetizations that we're extracting actually match the RISC-V semantics. And then the long-term goal is to actually integrate these proofs into Jolt's CI system, so that as the system evolves, it continues to be verified over time. So here's a little bit of background on Sail. Sail is a system developed by Cambridge, and it's a dependently typed DSL, domain-specific language, for specifying instruction set architectures. So at the top you can see all the models that have been developed in Sail. So you've got x86, ARM, RISC-V, etc. You can pass these models into Sail, and then Sail has a bunch of functionality. So you can extract simulators in C or in OCaml. You can do some automatic property-based testing of these architectures. And what we're focused on is you can extract to different theorem provers, such as Coq or Isabelle, and then prove properties about it. I guess one thing that you'll notice is there's no lean in this picture, so that's what we're aiming to develop. Just to give you a high-level idea of what Sail looks like, here's like a little bit of an excerpt of the RISC-V model. So here you can see it defines a nice way to convert between the bit code representation of, let's say, an XOR instruction. You can extract all the registers, and then you can define a semantics of this is what should happen when you execute the XOR instruction, right? So you're just reading from each register, performing the XOR instruction, and then writing back to that register, or to the destination register. So like I mentioned, we're building a backend in Sail for Lean, so this should allow you to extract any Sail model into Lean, and then once it's in Lean, this will give us a golden reference RISC-V semantics that we can prove equivalent to the Jolt machine. But in general, this should be useful for others as well who want to prove properties about Sail models in Lean. And again, this is in collaboration with Cambridge and Lindy Labs. So I'll mention some of the challenges that we've been running into in this conversion. One of them is that Lean doesn't have pattern guards, right? So you can see there's this like if condition on a pattern guard. So basically, this requires us to expand out these conditions, and this causes a bunch of like nested conditionals. So that was one thing we had to support. And then another thing is that Sail has a refinement type system, so it reasons about things like numerics automatically using an SMT solver. But once you convert these into like a dependently typed language like Lean, Lean's had a bit of a struggle to unify these dependent types automatically. So we've had to do some coercions and some wrappers around functions like bit vector append to make sure that the system actually compiles that we are extracting. So here's the current status of our RISC-V model. It's currently about 100,000 lines of code, and we're working on simplifying this and making it better. And we're down to 2 errors. This was much, much higher before, but there's like one more error around dealing with loops and mutating values. So since this is our reference semantics, we want to actually make sure it's correct. So instead of just blindly trusting our backend extraction, we want to test it. So we're using some standardized test suites for RISC-V. We're doing like some differential and property-based testing. And we're also integrating all this into Sail so that this stays correct over time as well. So I'll talk a little bit about zk Lean. So this is our DSL in Lean for representing zk statements. So the primary goal of the system is that we want it to be amenable to verification, and then also the automatic extraction of statements from other languages into Lean. So initially, we're supporting the systems that Jolt requires. So again, this is our own CS, lookup tables, and the composition of lookup tables. And the goal is to make the language easily extensible so that you can add other features that other backend systems might require. And I think already today we could probably support most systems like Plonk or Error or whatever your favorite backend is. Here's a little example of what the language looks like. It's a monadic language. So it's like you have this builder monad that allows you to construct your circuits. You can witness new field elements. So now this is like a field element in the circuit. And then you can add constraints. So it's like pretty basic here. Just you're asserting that x is either 0 or 1, right? Yeah, and then I guess one nice thing is it's polymorphic over the field, so it doesn't really matter. You can, whatever field you choose, it works for that. So in Jolt has subtables, or lookup tables, and it defines subtables by defining the multilinear extension of what the table is. So here you can see we have this function that defines a subtable from the multilinear extension, and all you have to do is give a lambda that defines how to evaluate the MLE. Yeah, I guess one thing additionally to note is that Jolt breaks up lookup tables into smaller lookup tables that are of size inputs 2 to the 8. And then it composes these smaller, like 8-bit lookup tables into larger lookup tables, like 32-bit lookup tables, by using these composition functions. So here's how you represent this in zklean. So you can see here you're defining these are all the subtables that you use for all the chunks of the 32-bit machine word. And then this function here declares how do you combine these things together to get the higher 32-bit representation. So the final part of our current effort is to automatically extract Jolt circuits into this zklean language that I just described. Jolt is implemented in Rust, so we want a way to automatically extract this so that as Jolt evolves, we can continue to get an updated representation. So we've implemented a Rust binary function that will link into Jolt's implementation as a library, and then this will automatically extract all the AST representations of the circuit, and then this outputs zklean as lean files on the file system, which you can then use to reason about. So at the top here, you can see this is like the Jolt Rust implementation of the, I think this is the eq subtable. Yeah, that's right. Yeah, and this is basically constraining that either x and y are both 0 or they're both 1. And then here you can see this is our automatic extraction into zklean. So we already have these representations available so that we can prove properties about them later. This is the extraction of what the R1CS constraints in Jolt look like. This is basically for each step of execution in the RISC-V model. You're given the current CPU state, so these are like a bunch of inputs like witness values, and it's nice that we can represent these in structs, so then if you want to reference like a given witness value, you can just like do a field access. So this is I think will be much more easy to reason about instead of just like an array of field elements or something like that. Yeah, and here you can see, this is constraining a flag to be 0 or 1. And then here's like a conditional of like combining a bunch of chunks, like all the 8-bit chunks into the 32-bit chunk. I guess one thing to mention is that we did find a small performance optimization already. So as we were doing our extraction, we noticed this subtable is being created. But the subtable was always returning 0, which is not actually useful for any computation. So we were actually able to remove this, and it gave us a small, like 2% improvement in Jolt. So small win already, but hopefully the verification effort will potentially lead to more. Yeah, so like I mentioned, our long-term goal is we want to integrate with Jolt CI. This will allow us to maintain the verification of Jolt over time as it evolves, and we can detect when theorems break. And maybe a future idea or dream is maybe these proofs can automatically be repaired using like AI techniques or tactics or SMT solvers. Yep. So here's a summary, I guess maybe more of like a picture of what we're aiming to do. So we have Jolt's code base in Rust. We extract it into zklean. Now we have the sail model of RISC-V, and we're extracting it also into lean, and then we're going to aim to develop this equivalence proof. So, thank you.
Any questions?
What is, maybe you can just succinctly clarify this for me, what's sort of the fundamental difference in purpose and what's included in zklean and zklib?
zklean is a lean library that allows you to encode like front-end statements, like and that kind of thing. And my understanding of zklib, it's more of a back-end focused system where they want to prove that the cryptographic implementations are correct.
Okay. Does zkLean depend on zklib or not at all?
No, we only depend on mathlib, which gives us like fields and maybe some theorems about them.
All right. Thank you.
Mhm.
Sorry, two basic questions. First, if I have other circuits that are not the Jolt VM, would zkLean essentially? So I guess what you're trying to do there in that right green box is just represent the Jolt circuit as you have a polynomial a multivariate polynomial representation of that. Is that what you ultimately?
So right now, zkLean is like representing the circuit. Right now we only support R1CS and these lookup tables in terms of like MLEs. So I guess, is there like a particular system you're thinking of that you want to?
So if I wanted to build a circuit for SHA-256, and then I wanted to prove that it was equivalent to some spec of SHA-256,
Great.
I would want to use that right column of yours, because I would have essentially a formal spec of SHA-256 comes from Wikipedia, and I would have a circuit, and I would like to do the equivalence proof. And I'm just wondering if you've built any of the infrastructure to help in that component. And then you can imagine, ECDSA and other components.
Yeah, so you would have to encode your circuit into zkLean, so like this part here, and then you'd have to have some reference implementation. So like you would probably write the spec, or maybe like this would be where like zkLib might come into play, where you have like the implementation of SHA in zkLib or something, and then you can prove that the circuit is enforcing.
How are you doing the equivalence? By some sort of refinement, or like? How are you planning to do it in that?
Yeah, so we define a semantics for zkLean. So like, this is what a circuit means, and then you can prove that the like evaluation of the circuit and all of its constraints are equivalent to whatever the reference is.
Have you compared your RISC-V formalization with the ones that have been used in Anger? I think of the one in ComCert, the one in SL4, the one in KCML. I once counted 4 different formalizations in ROC, and there might even be more. So 200 lines of code sounds like a lot, but maybe that's just because it's generated code.
Yeah, I think, so it's generated code. We're working on simplifying this. I think there's also things you can do to specialize, like, oh, this is a 32-bit machine, and we don't use these extensions, so we can throw them away. But I do think some of the handwritten specs are probably smaller, more simpler, more easier to reason about. But I do think maybe the SIL spec is more hardened, since it has been more battle tested.
I mean, SCL4 is used in industry quite widely. So
yeah, sure. Yeah.
Thanks.
Mm-hmm.
What do you think of the trade-offs between, say, having a higher level spec of some primitive like SHA-256 or ECDSA or whatever, and then proving equivalence between that and the Jolt circuit, and between that and RISC-V, versus proving equivalence between the circuit and some sequential reference like RISC-V directly? Because it seems to me that maybe your reference is going to use, it may already have optimizations, and it may use particular representations for the abstract variables, and you don't necessarily want to impose those choices on your circuit because they may require different trade-offs.
I'm not sure I followed the question. So I think as long as you have a representation of the, like a reference semantics, you should be able to prove it equivalent. I mean, if they are equivalent, but it might be like more or less amenable to the verification effort.
So on the slide you have the RISC-V model of whatever you're trying to prove equivalent in the circuit, right?
Mm-hmm.
Why that rather than a more abstract mathematical model of the primitive?
So I guess like the Jolt circuit is emulating the RISC-V machine. So the
okay.
so the RISC-V model is the thing we want the circuit to be equivalent to.
Okay.
How do you translate Rust to Lean, and why do you expect it to be correct?
So we build like a direct AST representation. So Jolt already has this for RNCS, so it's basically a pretty printer. And then the lookup tables, we can emulate the execution to build an AST, and then it's also just a printer. And then we also have tests that evaluate the MLE in Rust, and then the AST representation, and we can prove that those, or we execute them, test them to prove that they're equivalent. Yeah. So there is some. So it is part of the trusted computing base that we're pretty printing correct, but it's pretty, I think, reasonable to inspect it manually.
Yeah, you could consider using Aeneas or maybe Hex, or Virus is also thinking about a Lean backend.
Yeah. We looked into these tools, but we thought, at least with Jolt, we could easily get the AST ourselves, and reasoning about maybe the semantics that these tools require might make the proofs more difficult, but yeah, it's up for,
Yeah, you can do everything in one go.
yeah. Mm.
Anyone else?
So you said that you are planning to fix the theorem when something changed in the Rust side. How that works without breaking the theorem?
Yeah, so when say the Jolt front end changes, the CI will run our extraction again and then rerun the theorems. And if the theorems break, then like the CI will prevent the merging of the code before the theorems are fixed. Ideally, we have some automation that will like automatically fix the theorems as the front end changes, but that is maybe a future work kind of thing. So.
Anyone else? Okay, thank you very much.